I am pleased to introduce Inês Lynce for our talk. Inês Lynce is an associate professor at the University of Lisbon and a senior researcher in UNESCO. She's definitely a well-established researcher in the field of Boolean constraint solving and optimization. And you will notice that a lot of, let's say, state-of-the-art MaxSAT techniques were either developed by Inês Lynce or were somehow extensions of her work. Especially in the recent years, there have been other works apart from just MaxSAT, including various applications, like, for example, timetabling, and then other works like multi-objective MaxSAT, parallel solving, and so forth. So overall, I'm very excited that we can hear about MaxSAT directly from Inês Lynce. So thank you for accepting the invitation, and now I give the floor to you.
Thank you, Emir. I think you can all hear me well. So let's start with this talk. So first of all, thank you for this nice introduction and thank you for the invitation. It's my pleasure to be here. First, I have to say that at the beginning, I thought about speaking about a lot of things. Now things changed because we had this conference online. And so I have to say that I am one of those persons for whom it makes a huge difference to be in front of the public or in front of the computer, I'm afraid. So I'm used to give these kind of talks and to ask for people to interact and to see, to watch your eyes, to see if you are falling or not. So this will be quite, well, not the first, but somehow an experience. So I will introduce the basics of maximum satisfiability, but as Armin was saying at the end of his talk, it's much more what I am not talking about than what I'm really talking about. So if you can get intuition from the talk, of course. If you are really interested, you have to go and to dive into the papers and to work by yourself, okay? So first of all, let me make some acknowledgements. First of all, to the MaxSAT community. Well, before the MaxSAT community, to the SAT community, of course. But what I'm going to talk about is about scientific contributions in MaxSAT, where they are really in the SAT community, also the same in the SAT community. Sometimes practice comes before theory. And so solver developers have a really important role in this picture. Those who create instances, this is something also very important. You know that there are competitions and people run competitions, well, as something that is free, but it involves a lot of work, and I'm well aware of that. So if it was not for that, it would not be like that the success of SAT solvers. And also I have to acknowledge the slides that I'm using are partially based on the slides of João Marcos Silva, actually, with whom I collaborate, because this comes from a course that we teach in the University of Lisbon. So coming back to MaxSAT and coming back to the nice talk of Armin. So I remember, well, I started going to conferences in 2000, so it's 20 years now, and I was lucky enough because it was the time where SAT was only a workshop, not even a conference, and it was also when we started talking about competitions, and that was the impact of having competitions. The SAT competition has plenty of years of history, and then all the other related competitions, and you can see that in other fields. Of course, it was not, SAT was not the pioneer, but the way the competitions are run in the SAT community, that is a real achievement. By that time, you could hear talking about SAT, but my claim here, and is that there is life after SAT, of course, but the bases, SAT are the bases, and that is very important because somehow we come back to SAT. And why? Well, the success of SAT solvers, Armin have explained it a bit, but the point is that somehow if you are working with Booleans, somehow it is easier to improve it to the bit. And you have many people contributing, including undergrad students. And then when you go in upper level, so SAT is like programming an assembly, And then you go to higher levels where it's easier to encode the problems, but at the end you have to go to the machine level. So what is happening in MaxSAT and in other domains, so like SMT and so on, is that sometimes we use SAT solvers as a black box, and we somehow extend the techniques that are used in SAT, and this works quite well. And that is what I'm going to talk about the relation between MaxSAT and SAT. So first I will explain what are the overconstrained problems and where does MaxSAT come from. I will give a brief example. I could give many other examples, and well, that is one of the parts that I like the most in MaxSAT, and that I play the most in MaxSAT, is to say, well, we have a problem here, let's encode it and use MaxSAT to solve it. And what can be simple from an outside point of view, sometimes I see SAT not any longer as a SAT solver developer, not as someone coming from the outside and encoding a problem, but someone who likes to encode the problems, but that knows what is going on inside, and that takes some time to get this knowledge. But at the end, you see that how things work well is when you combine the knowledge of the solvers with the knowledge of the problem domain. Of course, this involves a team that can balance all the things, but at the end, if you think about the impact in society, you can do that with real applications. So let's start. Then I will talk about MaxSAT with iterative SAT solving. That's what we do in MaxSAT. We use SAT solvers a lot and iteratively. Then I will give you the overview of the MaxSAT algorithms, and I will tell you, this is what I'm going to talk about, this is what I'm not going to talk about, and so I can give you references if you want, and some pointers. Then I will talk about well, we have two important groups of solvers, the core guided and this last one, the MaxHS, and for that I will talk about what are the MUSes and MCSes. But so let's start. So I think we all, with the talk by Armin, we all get aware that we can have overconstrained problems when it is inconsistency. So the point is, SAT is a decision problem. The idea is either you can find a solution, or you say, and in that sense, you give a model, or you say there, I cannot satisfy this form. Okay, and so a set of constraints, for example, this formula here, if you apply resolution, this is in CNF following the talk on SAT. Of course, we don't need the CNF to explain that there are overconstrained problems. But here the point is that you pick the second and the third clause. You can, using resolution, you can infer not X1, and then again, using the resolution with the first clause, you derive the empty clause. So you can see clearly here that there are overconstrained problems. The point is that in SAT, when you find a solution, this is nice, you give the solution, of course, then you also can think about optimization, so that there are different qualities in different solutions, but then you can say, well, sometimes there is no solution, and then you can start thinking, depending on your background, in some kind of relaxation or approximations or whatsoever. But I think that at the end, overconstrained problems are as interesting as satisfiable problems, or even more interesting, because sometimes the modeler was expecting to have a problem that is not overconstrained, and then you have to try to understand what went wrong. So when we talk about overconstrained problems, and that's what we are going to talk about here, and we need to find an explanation. That's the point. Even if you have a modeler, someone who gave you the model, and you say, well, I cannot find you a solution. For example, suppose someone from biology that has built a model to explain the way, well, for example, like a virus is working and the interactions, and then you say, well, there is no solution given the observations, and you say, well, then my model cannot be right, and we have to think. And so it's not only say there is no solution, it's to give an explanation, okay? And it's not the explanation, then this has different names depending on the scientific fields, but the idea is not only giving an explanation, but for example, if you have a set of clauses, like in CNF, you have to say, well, there is this subset here of clauses that explain why I cannot find a solution. Of course, this looks simple and sometimes is not that simple. First, because you are interested in minimal or minimum explanations, because you can say, well, take the whole formula and this is not satisfiable. It can be the case that you cannot reduce the size, but usually if you have too many clauses, you are expecting to have a subset of those. And for example, the other point is that maybe you can have more than one source of unsatisfiability. And so there is not only one explanation, or maybe you find one explanation, then you try to solve that problem there, and then you have another explanation of unfeasibility. So for example, in this example here, in this formula here, that is an extension of the previous one, where you had all these first three clauses, and then you have the other two. You can see that these two clauses that I have added do not change the problem of being over-constrained, and so you can reduce the size to having only three clauses, okay? So this is the mindset here. You have an over-constrained problem, and you want somehow to fix it, either giving explanations, or let's see what we have here in MaxSAT. So this is one example. You can find another example here that is similar, where you have at the end two clauses that are doing nothing here, and we could continue. Now, a new concept that you have here is the concept of relaxation. And this is different. So the point is, well, the problem is over-constrained, okay. So I want to relax the problem, and the idea is I want to, well, in this case, to remove a few clauses. And here you have an example where at the end you can see that these three clauses were the ones responsible for the unfeasibility. So these three first clauses were the explanation, and now you only have two of them. So I think that this is clear, and you can imagine sets of clauses and how you can play with these sets. So let's see maximum satisfiability with an example. So now we call in CNF, we say usually broadly that a formula can be satisfiable or unsatisfiable, in the sense that you can find a solution or not. And in this case, you can have here, you can try, well, the idea of maximum satisfiability, and that is why the name, where the name comes from, is that you want to satisfy as many clauses as possible. So the problem of maximum satisfiability is to find the largest subset of clauses that is satisfied, okay? Of course, you can see the other way around, is to say the minimum is that you want to remove the smallest number of clauses. So that is the counterpart. And so given that you want to find the largest subset of clauses that is satisfiable, when you look at this example, you can see, well, you have these subsets here that correspond to explanations of unfeasibility. You can see in the first row that from the last two clauses you can derive not x2, and that from the first two clauses you can derive x2, and so here you have a problem. You can see something similar with the last row, and then with a few more steps you can realize that you have something similar with this group here on the right, okay? And so you can think, well, let's do the following. Let's remove one clause from each one of these sets, okay? But this is not the solution in maximum satisfiability, right? Anyone wants to come with a comment saying, what is the smallest number of clauses that we can remove to get this formula satisfiable? Feel free to use the chat or to speak out loud if you prefer. Come on. I'm teaching this very badly. Can we remove less than 3? Can we remove 2 clauses only? Getting back to this diagram here? I think we can, right? So the idea is that we somehow remove one clause from each of these sets, and then because there is intersection between these explanations, we can hitting sets. Good thing. That's how we will end, but that is the idea. Okay. Yes, we can have two by excluding. There are many possibilities, but the idea is that if we remove two clauses that belong to two of these subsets, that should be enough. So this is one example. We could have other examples, okay? But in this case, MaxSAT solution is 2, so the idea is to remove as few clauses as possible. Thank you for those who came forward. So the MaxSAT problems, you have a few variants. These are the ones which are well known and established. So the idea, first of all, we can have a distinction between what are called the hard clauses and the soft clauses, and also we can have weights on the soft clauses. So let's put this in words. What is the idea? The hard clauses are the ones that must be satisfied. So if we only have hard clauses, that is the traditional SAT problem, okay? So the idea is that we can separate between the hard clauses and the soft clauses. For example, if you think about timetabling, some of the things we can move, but for example, you cannot have two classes at the same time in the same room. So those are the kind of things that are hard clauses, okay? Soft clauses, for example, for one class, maybe it doesn't matter if it is in the morning or in the afternoon, that is fine. But that is the difference between having hard clauses and soft clauses. And then we have the problem of the weights. In the soft clauses, we can have weights or not. Either we consider all the constraints equally, all the soft clauses, or we don't. I will give you one example where the weights don't matter, so it would be the partial MaxSAT. Some of the techniques that I'm going to talk about can be and usually are extended to all variants of MaxSAT. Usually it's easier if I explain things either usually with partial MaxSAT or simply plain MaxSAT, where all the clauses are soft, okay? But we have ways to extend things or to adapt things. So now let's continue. So the goal is to compute, and this is a good point. It's not only the cost that you want to compute, because some of the algorithms you can be stuck in the cost but not be able to identify the clauses, but it's also the set of clauses that give you that cost. Okay, so let me talk about one simple problem that is quite intuitive and that it relates to an European project we have been involved. That is the problem of software package upgrades. So this was in 2010, so by then maybe SAT was not that well known. But for example, when we want to install a package, actually this was done in Debian. The idea is that there was an algorithm, not a very intelligent one, that would try to install your package, but sometimes there were broken dependencies, maybe things that were expected to continue working were no longer working. And so simply because in the end, heuristics were being used and not an exact algorithm where SAT would be less than, well, maybe less than 1 second to solve this kind of problems. So what we had a few packages that we want. So this is the maximum installability. If you not, in this case, is not the sense of having a system installed and wanting to make an upgrade, is when we want to install everything from scratch. So you have a Boolean variable to mention whether a package is installed or not. And then you have constraints associated with each package. So the idea is that we can have dependencies and we can have conflicts, in the sense that the dependencies are required packages and the conflicts are the disallowed packages, where I cannot have these two packages at the same time, 2 or more. And so the idea here is the problem of maximum installability, where you can install as many packages as you can, and you represent the package's constraints as hard clauses, otherwise at the end you'll have a problem. And you represent soft clauses. In this case, they are quite intuitive. one unit clause for each one of the packages, because you don't give different importance to different packages. In the cases where you can somehow have some priorities or preferences, then you can use the weights. And in practice, this, I know plain MaxSAT is the, or partial MaxSAT is the, usually it's something that appears as very appellative. From a user's point of view, if you have hundreds of thousands of solutions, you always must have a preference for some of them. But in this case, it's quite simple to understand what we have. So these are the packages constraints, and we translate this to MaxSAT. So we say, well, these are implications. If you have P1, then you must have P2 or P3. And if you have P1, you cannot have P4. That's one line for each one. And then you say, well, I want to install as many packages as possible. So that's how it works in MaxSAT. Usually it's not that easy, but that's how things work. Well, if you think in the prehistory of MaxSAT, the tradition was to apply branch and bound algorithms, where at the end you had the search tree and you would be updating the upper bound and the lower bound and trying to find a solution. Depending on the number of clauses you were able to satisfy at each point, at each node of the search. At some point you realized, and that was when things started, you realized that you could encode everything into SAT, and somehow the SAT solver will be much faster than dedicated algorithms. Okay, this is not a dogma, things can change, but that's how we see things these days. So the point is, well, let's play with MaxSAT using SAT solvers. And what we have been, also because in the prehistory of MaxSAT, the kind of instances that were used were randomly generated, so the branch and bound algorithms were more or less okay. When you start having instances that are somehow come from industry and are more complex in the sense that they are not randomly generated, then you realize that the branch and bound algorithms could not work very well, and that either you had to implement similar techniques of the one that were used in SAT, and actually pseudo-Boolean constraints that are, well, it's also related with SAT, but we have a lot of cardinality constraints. And you started realizing that you should use techniques similar to SAT. And so let's see how we can, this is an example. The idea is that for the cost of assignment, of course, is the sum of ways of falsified clauses. This is somehow an invariant. And then the point is that you relax each soft clause. Okay, so that is the point. When you have hard clauses, of course, they have to be satisfied. But if you have soft clauses, the idea is that you create a new literal. Well, at the end, it's a new variable, but these kind of literals, they have the ability to enable and disable clauses. So if you satisfy this literal here, the clause is trivially satisfied. But at the end, you only want to use these literals just in case you need them, okay? So this is quite simple. You have a lower bound, you can have an upper bound, and the idea is that you make the upper bound meet the optimum value. You can also think the other way around, okay? You can say, well, let's say if I can satisfy all the clauses, so the cost is 0, and so you start incrementing the cost. You also can do this. What happens is that at the end, this is, well, usually is the more appropriate approach, also depending on the kind of problem. But let's see how you can do it. So this variable here, y, it's only to keep track of the number of iterations. You start computing the upper bound by calling the SAT solver. So you say, let's forget about the idea of optimization in SAT solving. So let's get any kind of solution, okay? And so you say, well, now in the next iteration, I want to have a solution where I can improve the value of my upper bound, okay? And you say, well, I had this solution with cost 1,000, now let's see if I can reduce it, okay? And then you try to reduce, and at some point you cannot get a better solution. That's when you consider that you found the optimum value. What is amazing is that this works, okay? Because usually the SAT solver gets some freedom, it's able to find different solutions, and then the only thing is that that's why encoding cardinality constraints can be so important, because we are adding cardinality constraints to the MaxSAT encoding. So now let's have an overview of what we have in MaxSAT solving, and I can tell you, well, there are more, this is a mind map that could be enriched, and every year we have more variations. So for example, these days you can have incomplete max solvers in the sense that you have no guarantees, and at some point you have one solution but that is not guaranteed to be the best solution. And there are some approaches using local search for that, of course, but also the SAT solvers, the ones that guarantee to find the best solution if given enough time and memory. Only those ones these days tend to give, well, to say, well, this is the best solution that I have been able to find so far. Okay, and so that is also an interesting line of research. So at the end we had branch and bound, where we had no unit propagation, no closed learning. This was the traditional algorithm that is still working for randomly generated problem instances. Then we have the iterative MaxSAT algorithms, which are iterative in the sense that they make calls to a SAT solver. And in these cases, all the clauses are relaxed. That's what we have been. And we'll go afterwards to see what are the core guided algorithms and what is this idea of core guided. The core guided approaches are the ones that for practical industrial instances are considered to be the most effective. And I would say that, well, it's not a dogma, but this is still in place. So this is something that in the MaxSAT evaluation was clear in 2014 and is also clear, apart from what I have been telling you that is interesting, that we have, and in that case local search also plays an important role to have a solution, even if it's not the optimal one after some time. Okay, then we also have something that is interesting, that is iterative MaxHS, that actually relates with what something was talking about hitting sets. And I think that this approach is also very successful, also because there is plenty of research in hitting sets, and so somehow the algorithms have benefited from them. From that, and we also have model guided, that I think that after talking about these two, you will be able to realize what is model guided search, and you can find references about that. So let's now turn on the turbo so that we can see some of the algorithms in place. So what is the goal? You have seen what we have in iterative SAT solving is, please do not relax all the clauses. That is the worst case scenario. So what we see is something very, so the idea is that we don't need as many relaxation variables as the number of clauses. That is your expectation. And you can see, for example, that these two clauses here will never be used to explain why this formula is overconstrained. Okay, and so the idea is to relax the clauses on demand and to compute what are called, we have been talking about those explanations that are, that's why it's core guided MaxSAT is the unsatisfiable core. So let's see where is the core of the unfeasibility, and these are the core. So these are subset of clauses that are sufficient to explain the unsatisfiability. There are many alternative ways, but I will talk about the Fu and Malik's algorithm that was I would say the first successful, even though I will talk about another approach that in practice works better but builds on this approach. So the idea is that I call a SAT solver, and if the outcome, the status is unsat, then I have to start with a set of relaxation variables, and that starts empty, and that I will increase every time. And the idea is, if I have soft clauses in my core, that is this this set here, I will relax those clauses. And then at the end, I have to add this CNF set of clauses coming from the cardinality constraint, but I will illustrate this with an example. So this is our CNF formula, and what happens is that I identify this core, that this is the same form we have seen before, and we can say, well, if I have one core, when at least I have to get rid of one clause. And so what we do is that for all these clauses, we add the relaxation variables, these variables here, and I say, well, I want, I also add this cardinality constraint. So I can relax one of these clauses, not more than this. Okay, not more than one, because I know that it is enough to get rid of one of these clauses. Okay, and then what I see is that even if I relax one of these clauses, this will not be enough, because you still remember that we have three cores here. Okay, although there are some intersections, then I realize I can run the solver again, and I realize that I still have what is given to me now is another core. But now notice what happens. Some of the clauses get two relaxation variables, okay? Because I apply the same reasoning without taking into account whether the clauses already had or not relaxation variables, okay? The good thing is that I only have at most one constraints in terms of cardinalities constraints. So the instance is now set. A possible solutions you can have a look is to assign all variables value 1, all x variables, and we assign two of the relaxation variables value 1. That means that we get rid of two clauses, and so the MaxSAT solution is 10, so I can satisfy 10 out of 12 clauses. Important here, we only have at most one constraints being used, and the relaxed soft clauses remain soft, okay? And I continue adding relaxation variables if I want to. So, and some clauses are never relaxed. These two are the ones that we are not expecting to appear or to be responsible for the explanation. Okay, the MUSU3 algorithm came after and Fu and Malik's, but it made this algorithm to work in practice, and actually it makes a huge difference. What do we do here? We'll see an example running again, but the point is that in each one of the iterations, you have a new set here that you are building of relaxation clauses. So let's see what happens now, and also notice this, is that at some point we can turn some clauses which were soft, they can become hard. So let's see how this works. So the beginning, exactly the same thing. I get one unsat core, and then I have to add the relaxation variable. So far, we have exactly the same approach. Things change when I ask for another core, and imagine that I get exactly the same answer. And now we have done something similar. So see that we had, oh, okay, good. You can see that we had exactly the same core. The thing is that instead, have a look at the relaxation variables and notice that we only have one relaxation variable for each one of the clauses, okay, no more than that. And then the instance is now set, and if you have a look also the cardinality constraint that we have here, while before we only had less or equal than 1, now you have less or equal than 2 or 3, or the number of calls that you are performing. Okay, so the main difference that you can see here is that we have at most k constraints, and of course this in terms of encoding to CNF is more challenging. Also, the relaxed soft clauses can become hard. So this somehow makes the answer to relax always the same clauses. If you move these clauses to become hard, and here this is the same, some clauses are not relaxed. Okay, so this is the basis of the core guided algorithms. And now I will introduce some concepts. Actually, MUSes and MCSes, you can see these only in the context, you can forget about MaxSAT, but at the end, we'll see that this has everything to do with MaxSAT. So what are these MUSes and MCSes? This is what we have. We are going back to the beginning of the talk, where you have a formula that is overconstrained, and we want to have some to know if the formula is minimally unsatisfiable or not. So when a formula is unsatisfiable, you can say, well, where is the reason, where is the explanation? And you can see that in this case, we already have in our mind this example running, and you can say that, well, now we have three subsets of unsatisfiable subformulas that are minimally unsatisfiable, and we can pick, for example, this one is minimally unsatisfiable, and you can get rid of all the others. So these days, even at the beginning, some years ago, we should call this the unsatisfiable course. These days, the more formal ways to talk about minimal unsatisfiable subformulas, okay? And of course, we can formalize this and say, well, the idea is that it's minimally unsatisfiable in the sense that if you remove any of the clauses of the MUS, then the formula becomes satisfiable. So that is the point here. And you can see here an example where you say, well, you have this MUS here, only this part of the clause. And if you remove any of these three clauses, of course, this subset is no longer unsatisfiable. And then you have the other counterpart, that is the minimal correction subset. That is the other way around. So if the idea is that we have a formula, you assume also that the formula is unsatisfiable. And the idea is that if you remove C from F, that's the point here, then the formula becomes satisfiable, okay? And the point is that you had to remove those clauses in C so that the formula becomes satisfiable, and you really need to remove those clauses if it was a subset, the formula would be unsatisfiable. That's what we have here, okay? And you can have a look at what we had before, and for sure, one of the three first clauses has to be removed, okay? In here, we have not mentioned this, but we also have another unsatisfiable. Actually, the last clause is not relevant, but also here you have an MUS. And so at the end, when you want the minimal correction subset, we have to break somehow all the MUSs. And this is what we can find is the duality between MUSs and MCSs. And that's what we'll see implemented in the MaxHS algorithm. So we'll talk about the hitting sets, the ones that someone at the beginning mentioned, and what is the idea of the hitting sets, and we'll make the bridge with the MUSs and MCSs, is that if you have, well, we have a finite set, okay, here with integers, so that this is a clear example, but you can imagine that these are clauses. And you have a set of subsets, right? And now you can imagine that you have MUSs, although the other way around also works. Okay, so imagine you have all these clauses and you can identify here these MUSs, okay? And notice that we have one intersection, well, two intersections actually. You have number 3 in the first set and the second one, and number 5 in the second subset and the third one, okay? And what is the idea of a hitting set? So the idea, well, I think the name is clear, only the name, well, per se is already clear. The idea is that I have to hit all the sets in F, okay? So the intersection, if you pick each one of the members of F, each one of these subsets, if you make the intersection with G, it has to be different from the empty set, so you need to have. Of course, you won't have a subset to be minimal. The idea is that you cannot reduce them. but here you can see that the first set, well, is a hitting set, H1, but on the other hand, you can get rid of some of the numbers you had. And for example, you can pick 2 from the first set, 4 from the second, and 6 from the third set, but then it's not cardinality minimal because we have noticed that there was some intersections and that's where we can gain. And so if you pick the number 3, you can get rid of these 2. Well, we have hit the first and the second subset, and then we pick 7 for the third subset. Okay, so this happened with MUSes and MCSes. So this is quite interesting. Some of you, depending of your background, could see it from the very beginning. But the idea is that MUSes are minimal hitting sets of MCSes and the other way around. Okay, so if you see this formula here, but that is not what matters the most, you can simply look at these numbers here. And you can see the MUSes here. You can see that all the MCSes are possible hitting sets for the MUSes. Of course, if you want the ones that are cardinality minimal, only the 2 first work. Okay, and you also can see the other way around. So if you pick this first MUS, that actually is the cardinal, is in terms of cardinality is the smallest, you can see that all the MCSes either have C1 or C2. Okay, so this is something that has been noticed, and of course this is something that is intuitive, but you can also see that if it was not the case, you would have a contradiction. I would not waste much time on this also because it's intuitive. So let's finish with the MaxHS approach for MaxSAT. So the remark is that the MaxSAT solution is the smallest MCS. I think this is clear now for everyone. And any MCS is a hitting set of all the MUSes. So given this, you can say, well, let's compute all the MUSes and then have hitting sets, the smallest hitting sets. Then you have the MCS and we are done. Okay? So this, of course, in theory, this works. What is amazing, let me go forward, is that this is quite effective in practice, right? So what is the idea? You have kappa is a set of unsatisfiable cores that you construct over time, okay? And then you try to find a minimum hitting set. You can make use of very nice and very effective algorithms that have been developed over years. And then you check the satisfiability. If it is satisfied, that means that you have found all the MUSes and so you have the MCS. Otherwise, you have to compute more MUSes, right? So let's give you an example before finishing. This is the idea. We start with no MUSes. This is the example that you have been looking at for some time now. And the idea is, well, let's see, can I have a satisfiable formula? Of course, no. You have to remove some of these clauses. So give me a core, please. And you have C1, C2, C3, and C4. And so we have to update kappa with this new core, and then you have to find a hitting set. And C1 is fine, but then you realize that removing C1 is not enough because you have more than one unsatisfiable core, and you ask for another core. In this case, it will be the last row here, and you update K, and you find a minimal hitting set. And so you pick C1 and C9, okay? And now you can see that this is not enough. Maybe if you were lucky enough to have picked some other 2 clauses, this would be working. And then you find the other MUS. You realize that you don't have to enumerate all the MUSes when you have intersections. At some point you can be lucky, I would say. So you update kappa, and then you find C4 and C9, which are here, C4 and C9. And then, of course, the formula is satisfiable. You terminate and you return 2. And this is quite nice because it's an alternative approach and sometimes it also works very well. So to sum up that I have run out of time. So we have talked about overconstrained problems and of course maximum satisfiability. MaxSAT with iterative SAT solving. So this is a good way to go. I'm not saying there are no alternatives, but this is what is the winner these days. Mostly, of course, it depends on the domain. So if this does not work, don't give up. So try alternative approaches. This is more or less standard, but of course it depends on the, and it's nice to have problem instances that cannot be traditionally solved the traditional way. We have talked about the core guided MaxSAT, where you identify the MUSes, and then about MaxHS that realizes, puts in practice the idea of the complementary duality between MUSes and MCSes. And I am done. Thank you very much.
Okay, so we reached the end of the talk. So thank you, Inês, for this for the talk. So I guess we have a round of applause. It doesn't work that well over internet, but it is what it is. Excellent, excellent. So I'm happy we had some help from the audience. Okay, great. So now is the time for Q&A. And during the talk, there was actually a question, which I will now read out and also ask just a follow-up on that question. So one user, we have a question from an anonymous person asking about whether at most K constraints, can they be efficiently encoded in CNF? Because maybe it exponentially blows up. And whether, and I would like to ask whether MaxSAT solvers have some kind of native support for cardinality constraints. So why are we converting them to CNF and not maybe natively handling them in some way?
Okay, so I see the question, yes. So let me put, what we have seen here is that, and I think that MaxHS algorithm, it's quite clear if you have a look, is that sometimes what in terms of complexity is in terms of worst case is worse than alternative approaches. In practice, it can work. And actually that is what we see in SAT, of course. So SAT is exponential in the worst case, but Armin has talked about SAT as if it was something easy. That is not, okay? So that's real. So in terms of, there is huge work with respect to cardinality, encoding cardinality constraints into CNF. I agree that sometimes you can somehow treat them natively and not to convert them into CNF. There are smart ways to convert them. Actually, I have not talked about this, but I have been involved in OpenWBO. That is a MaxSAT solver that is open source, and that has the nice thing that you can play with different cardinality constraints, different encodings of cardinality constraints, and also you can use different SAT solvers inside, and it's up to the user to make the experiments with it, because we realize, well, we are not talking about different SAT solvers here because that would be a whole new world, but also in terms of cardinality constraints, these are bottlenecks when we think about encoding things into SAT. So for example, there are incremental encodings. For example, this is something that plays very well, but the point here is that sometimes what seems to be, even if you have something that seems to be in the worst case, it's not promising, sometimes it is worth trying, because you have to realize that unless you generate a problem instance randomly, and then in terms of probabilities, it usually, if you make the in terms of complexity, the analysis, it makes sense. When you have problem instances that come for industry, the idea is that they are biased, okay? So it can be the case that, well, these cardinality constraints work well in these cases, and you don't know if that instance, well, sometimes there are some kind of tools, and of course you can even use machine learning for that to realize what is the best encoding in terms of cardinality constraints, depending on the problem you are handling. But then you know that it's not only that. So it's the whole structure of the problem. But well, my message here is even if sometimes in terms of complexity you have some approach or some algorithms that are not that promising, that does not mean that in practice it's not the case that they pay off. So what we see here in MaxSAT is that many times it's from the competitions that you get the intuition rather than looking at the complexity. Of course, that everything has its place. The only thing is that it's not only looking at the complexity analysis that we see the behavior of the solvers. That's the point. Okay. I see that the number of questions is increasing.
So we have a number of questions. So we have a question from Madalena Erascu. The question is to compare MaxSAT and SMT. So when should we use MaxSAT and when should we deal with SMT? So what are they then, like kind of the key elements that we know?
Yes. So my point is, if you can use SAT, don't use MaxSAT, right? So there is no point in using MaxSAT if you have a decision problem, although it's quite clear the difference between MaxSAT and SAT. So the point is, if you can use MaxSAT, don't use SMT. But that depends on the effort you make on the encoding, okay? Well, my experience is more on sometimes using ASP, because even for students is quite, or even CSP or SMT, it's a bit more tricky. But the point is, sometimes if it's the first approach of someone, don't give them SAT, please, because that is quite scary. On the other hand, if performance is an issue, then you should use SAT or MaxSAT or whatever. So SMT depends on the problem. So if you really need, for example, if you need integers, well, if you want, it depends on the domains, but I'm not saying that SAT solves and MaxSAT all the problems of the world. You have to be reasonable. So it depends on the time you want to invest on the encoding, and that depends on the size of the problems you have to handle. And it depends, for example, if you have a theory in SMT that is quite appropriate for the problem you are handling, don't try to translate everything to MaxSAT, for example. So I can see that, but of course, when you have a hammer, you then try to put that thing in that perspective. That also depends on your background. Okay, so I've been working in SAT before working on MaxSAT. Of course, for me, everything is MaxSAT, quite intuitive. But for example, I learned that for students, depending on the time they have for their projects, you should not put students working directly on SAT unless you want to kill them, or it depends. Some will survive, but some others may start hating, because even, for example, Armin talked about that. The CNF encoding, it's not a nice encoding, right? When you have so it's a matter of, is it critical or not, the time? If it's not critical, use a higher level language. That's the point. If time is critical, that's what I was saying. My experience in some of the problems that we have been playing with, that we look at them and we see MaxSAT, and in the past they were solved using answer set programming. Usually we get better performance using MaxSAT, but that means that we are used to use MaxSAT. And of course, it depends on the price you want to pay. If you want to prototype and to have a nice answer and it to be fast, then I would not go for MaxSAT. So that's how I see things. Or if SMT is more appropriate, these are not different religions. I mean.
Okay, so it seems like we have 3 questions related to the weights for MaxSAT problems.
Okay.
One by Kevin Dahlmeyer is asking whether the algorithms you described, can they be used in the weighted
Yes, they can. Yes. And actually they are available for weighted MaxSAT. Okay.
And then who asks about, for example, does it make a difference if we have rational weights? For example, what happens?
Yes, so we assume that we have, that makes a difference, yes. But the point here is it depends on the kind of problem you are playing with. Okay, so usually you assume that you have integers and some nice things that you can have. So for example, we realize that many MaxSAT problems, you can identify lexicographic orderings, even though people encode them by hand and do not realize. So sometimes you see that people tend to encode problems in a way that are not that is not the simplest way. And that's why, for example, compared with CSP and ASP, the fact that you are strict to CNF sometimes is a risk that you have to take. So it's quite nice because it's easy to run different solvers on the same problem instance. On the other hand, you can, for example, some problems are much more intuitive if you encode them into DNF, but we use CNF. So that's why sometimes you have to be careful about that. But in the sense that we have weighted, yes, you can have weighted. Usually we assume that we have integers. And what we can see is we have some problems that we have weights, but they are not. So in partial MaxSAT, you can have plenty of problem instances to play with. Of course, at some point, and if you think about preferences, for example, you need weights. So that's the point. But yes, this can be extended and have been extended. Okay.
But the MaxHS algorithm you described, it seems like it doesn't necessarily need integers. It can also be floats.
Yes, yes, that's right.
And there was another question by Thomas Shiex, is how does the order of the weights matter? So for example, can we have, what are the best algorithms to handle very large weights? So for example, over 32 bits or more.
We have a problem with that. In practice, I'm not sure if MaxSAT pays that much when you have those very large weights. So we have to be careful about that. Sometimes, well, and this is CPAIOR, so in OR you have very good techniques. So it's not, even in our team, we are not strict to, we have a problem and we want to solve that problem. That's the beginning. And then we have the know-how in MaxSAT, but I don't think that we have very large weights. You can, somehow you should have a kind of an abstraction before going to either to have subsets of the problem or whatsoever. So we actually have a paper at CPAIOR in timetabling, and we have to do a lot of tricky things before feeding the MaxSAT solver. So that's what we realize these days.
Yeah, so if we have like very large weights, we should probably look at somehow how to massage that and pre-process it.
Yes,
maybe.
that's it. That's it. That's the message.
And what's interesting about this kind of MaxSAT approach is that a set itself is NP complete. So we're going to execute a set solver as an oracle. So all of these are like theoretically exponentially called. And then this brings the question that Ronald Yap asks is, which approach is theoretically superior? So do we have some kind of guarantee that maybe one approach is theoretically better than the other, given that they all use somehow this oracle in between?
Yes, you have results on them, actually. My point here is, for example, we have not talked about that. But for example, in terms of MUSes, for example, we have not discussed this, but we have very different algorithms for identifying MUSes. What we have seen, and we see that in many papers publishing results on identifying MUSes, is that sometimes in terms of theoretical results, you have one thing, in terms of practical results, you have another. You have that, you have those results. Actually, there is very good work on that. But on the other hand, I would not fit very tight to those results. Okay. I see also there is a comment. Well, I'm not the chair of the session. Thomas saying with large weights and floating points are very similar. That's it's a matter of scaling, right? Right. But we see, well, we can say that even in MaxSAT, we clearly know that there are limitations. So that's the point. But the same way that we see that there was a paradigm shift when we started solving MaxSAT using SAT solvers as an oracle, that has made a tremendous change. I'm not, well, I would say that some of the things can, in terms of paradigm, are changing. I don't see such a change, but they can happen. So it can be a matter of time, yes, but also the other approaches are improving in other areas. So.
Okay, so Thomas says thanks. And just maybe one more question before we conclude by Simon is asking is whether core-guided approaches are efficient in finding good solutions rapidly. So can it quickly find some good solutions?
Yes, what we see is that we can find good solutions rapidly, but then the way it's well, let me see if I can make this clear. Sometimes, suppose you have, you can find them clearly, but then if you give more time, it's not that clear if that solution improves over time. So that is my point. Sometimes you see that the core guided somehow gets stuck and is not, but sometimes for having a good solution, it's okay. For proving that, for finding the optimal solution, it takes more time and sometimes it's not even close to the optimal solution. So there, regarding what Simon is asking, that is something that is more recent in MaxSAT, in the community, is to be worried about giving a good solution in a short time. And I think there is still place for them. Actually, Alexander Nadel has a nice solver that actually uses OpenWBO. And I think that, well, I'm not sure if the last version is still, so maybe I'm wrong. But I know that Alexander has a very nice solver where the idea is that you want to give a nice solution rapidly. So there are approaches for that, but that is something that is the community is worried about in the last few years. So I think there is still place for improvement there.
Okay, great. So I think we're now just on time. I think now we'll try to conclude the session. So thank you, Inês, for this lovely presentation.
Thank you very much.
And we're very happy to see that we had over 150 people attending the talk and also had lots of questions.